Ever stop and wonder how our computers got so mind-bogglingly fast? It's not just about brute force or raw power. It's about being clever. Today, we're pulling back the curtain on a technique called pipelining. It's the secret sauce that lets modern processors work smarter, not just harder. Let's jump in.
So this is the big question, right? It's the puzzle that keeps chip designers up at night. You can't just crank up the speed forever. Things get too hot, too complicated. So how do you squeeze more and more performance out of that little piece of silicon? Turns out, the answer isn't about working faster. It's about working smarter. And to get our heads around this, just picture a factory assembly line. Instead of one person trying to build an entire car from scratch, the work gets broken down into these small, specialized steps. Well, that exact idea, that simple shift in thinking, is the core concept behind CPU pipelining. See, the old way of doing things was, well, simple, but really slow. The CPU would take a single instruction, do everything from start to finish, and only then would it even look at the next one. But the new way, it's so much smarter. It overlaps all these tasks, starting a new instruction before the last one is even finished. And this visual just makes it crystal clear. First, look at the non-pipeline section. Instruction 1 takes 4 clock cycles. Instruction 2 can't even begin until cycle 5. You're looking at a total of 8 cycles for just 2 instructions. Now, check out the pipeline side. It's like magic. By overlapping the steps, we finish both instructions in just 5 clock cycles. We're doing the exact same amount of work in nearly half the time. So let's put a proper definition on it. Pipelining is all about splitting an instruction's journey into separate stages. This lets the processor juggle multiple instructions at the very same time, where each one is just at a different point on the assembly line. The key word here, and the whole point of this, is throughput. You're just getting way more work done in the same amount of time. Okay, so what exactly are these stages on our little CPU assembly line? Let's trace the journey of one instruction as it zips through the pipeline. There are 4 main steps. First up is fetch, which is literally just the CPU grabbing the instruction from memory. Then comes decode, where the CPU figures out, okay, what am I actually supposed to do here? Third is execute. This is where the real work, the calculation, happens. And finally, write back, where the results of all that work gets saved. And this is such an important point to lock in. Pipelining didn't invent some brand new way to process instructions. All that classic fetch, decode, execute stuff is still there. All pipelining does is provide a genius way of organizing the work so we can run these cycles for multiple instructions all at once in this beautiful, overlapping dance. Let's walk through this, because this is where you really see the power. Cycle 1, instruction A gets fetched. Simple enough. Cycle 2, A moves to decode, and at the same time, instruction B gets fetched. Now fast forward to cycle 4, look at that. We have 4 different instructions all in the pipeline at the same time, each in a different stage. The result is just incredible. Instruction A finishes on cycle 4, B on 5, C on 6, and D on 7. That's 4 instructions done in only 7 cycles. Without the pipeline, this would have taken a massive 16 cycles. Okay, so this idea is already incredibly powerful by itself. But what happens when you take this super efficient assembly line and you build an entire factory filled with them, all running at once? Well, that's exactly what a modern multi-core processor is. It's a pretty elegant idea, really. If one pipeline is one efficient assembly line, then a multi-core processor is just a factory that has 2 or 4 or 8 or even more of these assembly lines, each one working independently. And this combination is what makes modern computing possible. Each individual core is made super efficient by its own pipeline. Then, having multiple cores means you have more of these efficient workers to throw at a problem. This is how your computer can be streaming a 4K video, running a demanding game, and downloading a huge file all at the same time without even breaking a sweat. It's true parallel processing. But, just like any complex machine, it's not always a perfectly smooth ride. Sometimes that assembly line can get jammed up. It's really important to understand that even this amazing technique has its limits. Yeah, these are called pipelining hazards. For instance, what happens if instruction 2 needs the answer from instruction 1, but instruction 1 isn't finished yet? Well, the whole assembly line has to hit the brakes and stall until that result is ready. Or another classic one, what if the program suddenly needs to jump to a totally different section of code? All those instructions you've already loaded into the pipeline, they're useless now. They have to get flushed out, and that wastes time. These little hazards are the reason a 4-stage pipeline doesn't magically give you a 4 times speed up in the real world. So let's bring it all home. The story of modern computer performance isn't about one single trick. It's really about two huge ideas working together in perfect harmony. And if you take away one thing from all this, it's this right here. Pipelining is about making each individual worker, each core, way more efficient by overlapping its tasks. Multi-core is simply about putting more of those hyper-efficient workers on the job. And here's the really precise way to say it. Pipelining boosts throughput by overlapping stages inside one core. Multi-core boosts parallelism by adding more cores to the whole chip. They're two different but deeply connected ideas that, together, give us the amazing performance we rely on every single day.
You know, pipelining was a revolutionary trick, and it's still absolutely fundamental to how computers work. But as engineers keep packing billions and billions of transistors onto a tiny chip, pushing the very limits of physics, you have to wonder, what's the next great trick going to be? What's the next leap forward that will completely redefine what our machines can do?